In the remaining sections in Chapter 15, we talk about random number generators. And this is a good place to put this particular topic that is in the same chapter with the do loops, because do loops can facilitate the selection of a random sample. And so whenever we do any kind of a random number generation, it requires the use of a seed value. Seed values can be anything between 0 and 2 to the 31st power and then -1. So very large numbers can be used then as seed values. We will look at two types of random number generators, some that are referred to as a SAS function and the others referred to as a call routine. They both use seed values. They manage their seed values a little bit differently. The one initial piece of advice whenever you do look at seed values, even though 0 is a possibility, the selection of seed value 0 is the computer's clock. And I don't recommend doing that, because the idea that whenever you draw the random sample you need to have some record of the random selection, and so specifying the seed value does that. That is, it provides that reproducibility. So you don't have to keep all of the randomly selected items. You can just record the seed value so long as you don't change the rest of the functions around that seed value. Very often we talk about our data coming from a normal distribution. So it seems logical for us to start then with our distribution, a standard normal distribution. So that, recall, a standard normal distribution, mean of 0, variance of 1, and we're looking at values that are typically between -3 and +3. That's going to contain almost all of the results from a standard normal distribution. Now, different than what we looked at in one of the earlier chapters where you had prob norm and probit. So prob norm determined probabilities associated with a normal distribution, and probit determined critical values that were associated with specific probabilities. This is different. This is saying that given we have this standard normal distribution, make a random selection of values. Then previously we called those a z-score, or you may have seen that in your textbooks for your statistical methods classes. So we're going to look at two different approaches here. First is a function. The function for generating a random value from a standard normal distribution is ranor, and then you specify the seed. And so, like the other functions earlier in this book, in the data step, you would have a new variable assignment equals ranor and then a seed value. So the 2816 is just the value I happen to choose to generate this value y that is chosen from a standard normal distribution. Separate or from a ranor function is a call routine. There are many different call routines, and so for random number generation, here is you can call a random number from a standard normal distribution. The arguments inside of this call routine are the seed value, comma, and the x value. The x value is the value returned to you, that is the randomly generated value from that standard normal distribution. And so that we'll look at objective 15.7 in SAS. In objective 15.7, we can demonstrate the control one has over the seed values used in random number generation. Not all seed values start out the same. So here, where I've selected seeds 1, 2, and 3 at values 21, 20, that's just, I wanted them all to start at the same place, and I'm utilizing them a little bit differently. We're going to look at what kind of random sample the call routine generates using those two seed values, and we'll call those values that come out of the call routine x1 and x2 respectively. y1 and y2 are going to be values associated with the ranor function. One where we use the variable seed3 to read into the ranor function, and in the ranor function we can also put the seed value in as the argument here. I have a do loop, this do statement here, So this says do from I equals 1 to 10. I'm going to generate 4 values and then an end. So this is I'm generating a sample of size 10 using each of these different approaches. I did something here a little bit differently than 2, just to see what's going on with the seed values. Once it gets to the 6th iteration, then do. So this is a different application of a do loop than we've seen before. So if then do, that do would require an end as well. So I have nested do loops, but this one's conditional. It'll only operate whenever the counter or indexing variable gets to 6. And so that if we execute this, I just look at a print of the data points. Selected. So I have my 10 observations here, the seed values. Okay, so they were all set at 2120, and so seed 3 stayed there, but so seed 1 goes into the call routine, seed 2 goes into a call routine, and so you can see how those things are changing from one item to the next. Has our indexing variable or counter variable here, and then the results from the call routine. And so if we look at x1, x2, and y1, those are all the same value. Since they all started with the same number, 2120, they did some manipulation of 2120 before it ran that function or got into that call routine. And y2 is just typing the seed value directly into the ran/or function. Now with the call routine, you cannot type the number in. You have to enter it in as a variable, such as I have here. And then you can just see how they handle things a little bit differently. I put the information in here about resetting the seed value just to see what's going to happen in each of these. And so it was just seeds 2 and 3 that I changed here. So if I would have left things go, we see that they were the seeds 1 and seed 2. The call routines were managing things the same way. So you can change up the data set as you go along here. So this is just a demonstration on how seed values can be managed. For most of us, we're probably just going to pick one, either a call routine or a ran/or function, whichever one we're more comfortable with, and that's the thing we're going to use. So starting out, the beginning programmer, I think you probably would favor the ran/or function over a call routine, but we'll look at both. Like the probability distributions we spoke about earlier in the book, we had continuous distributions and discrete distributions, and likewise we have random number generation for continuous distributions and discrete distributions. And so for the continuous distributions, we'll just look at the normal distribution and a uniform distribution. Excuse me. So here we're looking at do statement with an end. I'm generating a random sample of size 10, and so what are each one of these steps doing here is what we want to look at in this particular arrangement here. So x, I'm just using ran/or function in each of these. I can change the seed values any way I wish here. So x is this is going to generate a standard normal random variable. If I add 5 to this is a standard normal random variable, and so if I generate a standard normal and add 5 to it, then that means I'm changing the mean from 0 to 5. Let me line those up. That looks a little better. Okay, by the addition of 5 to, I've not done anything to the variance. So you can think about this like having a normal curve and you've just picked it up and moved it over 5 units. Whenever you multiply a standard normal or a continuous random variable, you affect its variance. And so here, square root of 6 times a random normal, a number from the ran/or function, a standard normal variable. So if all I'm doing is multiplying by 6, I'm changing the variance. And so instead of having variance 1, now I have variance 6 because this was square root 6. So if you, again, instead of picking it up and moving it over, we're leaving the distribution centered at 0 and multiplying by square root 6, we're increasing the variability. So we're just stretching that curve but maintaining the center at 0. Or you can do both. You can look at the multiplying the standard normal to change the variance, so square this value to get the new variance, and then once you change the dispersion of it, then you move it the mean according to whatever you add or subtract. So then you take that stretch distribution and locate it 8 units over. So whenever we run this, then this is the previous objective we're seeing here above. When we run this, then I have the values x, y, w, and u that correspond to these that we've generated in here, all with the RANOR function. In your book, there are some listings here of simple arithmetic functions then, and what they do to the distributions that we are generating. So that's true not just for standard normal, but for any distribution. Additionally, there are random number generators for Cauchy, exponential, and gamma distributions. Those are kind of beyond the scope of what we're doing here, but more useful to you might be the uniform distribution. And so you can use a function for this, or a call routine, ran uni, and so this generates a uniform distribution on the interval 0 to 1. And so here, using these arithmetic operations in the list below that uniform distribution introduction, again, you can take a uniform distribution, pick it up, move it over. You can stretch it or shrink it. If a is larger than 1, then you would shrink it. And so that you can make changes then to the distribution. It depends on the order. If you move it before, if you move the mean before you multiply, or here this says stretch the distribution and then add the beta value to it to change the mean. And as I'm going through this here, this is written as A, and A is in the description, except then there's a typo here that's written as alpha in these. So given that I've got beta in the others, those A's should probably be alphas. An additional exercise or option to this objective 15.8 would be to change these to ran uni, and you can observe what happens to those distributions as well. We can also select random numbers from discrete distributions, and so here I have a binomial distribution. So recall our probability functions. We had prob binomial, which computed cumulative probabilities for binomial random variables. This says that we describe the population as having a binomial distribution. Now draw a random sample from that. Likewise, we had the Poisson distribution, and so we can also draw a random sample from a Poisson distribution using either random number generation functions or call routines. For a Poisson distribution, you do have to know the mean of the distribution, and in the binomial distribution we had to know the probability as well as the number of trials. So you study both of these to learn the orders. You can have a tabled probability distribution. So this, if it's just a discrete distribution where these values for the probabilities, I have n different probabilities here, and so that those can be specified so that each of these p-values in here is between 0 and 1, and that they must add up to 1. And so the random number generated from that distribution is given by x. Okay, and that's the x is the same that occurs here. So you notice the order of the operations, and then the output variable from the call routine is listed last in all of these. In Objective 15.9, the number of calls received at the Technology Support Desk of a local computer store is described by a Poisson distribution with an average of 14 calls per day. Generate 2 random samples of size 5 days For a random variable C, the number of daily calls. Compute the average of C for each of the random samples using the means procedure. So here I have two samples, 1 and 2. Each sample 1 contains 5 days, sample 2 contains a different 5 days, and these run then in nested do loops. So from earlier in the chapter, each do statement has an end, and we want it to write down what's happening at every iteration, so that output statement belongs in here. So this is the random number generator for the Poisson distribution, the seed value, and it said that we had an average of 14 calls per day, so that's the parameter 14 associated with this distribution. Then proc means for each sample, and then C is what we're looking at for our variable. That's what came out of this function up here. And so that's one way I can do the means portion of this. You could also, I use the class for sample. That did not require things be sorted. Here I use the by sample statement here. Since sample was in the outer loop, then I didn't have to sort. It was already put in order. So if I put these together and run them, okay, I have option 1 and option 2 just for the means procedure. Notice in the program I didn't ask it to write any of the data down. I could have done that with a proc print, or I can move to the Explorer window and look at View Table to view the contents of data set 9. Either way we have done this, we get the same information in each of these. So it's just what configuration do you want the data to be in. We could probably also look at some of the reports that we've done in the past, maybe on means and using the report procedure. We wouldn't have as many statistics available to us. We just accepted the default statistics. So think about all the things you could have asked for from the means procedure that could have been calculated. Also, we kept things very manageable and only working with samples of size 5. Okay, so you could generate 2 samples of size 500 quite easily. I would not recommend doing proc print with that, but then you can go ahead and look at each one of the means procedures. You can look at graphics options. You can do also, bring these data sets that you're creating in this way. You can bring those into any of the previous procedures we've spoken about.